Hello and welcome to our latest webinar on physical stability of agrochemical formulations. My name is Carmen Guguta and I'm the product manager of Technobis crystallization systems. Speaking today will be Dr. Martin Viertelhaus, who's a research scientist, crystalline materials and polymorphism at BASF, Germany. This webinar will last about 45 minutes and it's being recorded. The record will be made available to you as participants afterwards. If you have any questions, please send them to info@crystallizationsystems.com or use the chat from this webinar. You will be muted just to prevent some background noise. I will start with a bit about Technobis crystallization systems. We are a privately owned company located in Alkmaar, the Netherlands. We are busy in several markets, active in pharma, agrochemicals, fine chemicals, military, fuel research, food and personal care. Technobis Crystallization Systems is a world-leading technology provider for solid-state research, process development and formulation. Our portfolio includes 3 systems: the Crystal Breeder, Crystal 16 and Crystal Line. These 3 instruments are bringing to you technology that enables you to look into stability of formulation, control of crystal habit, process optimization type of studies, solubility determinations, phase diagrams, polymorph, salt, cold crystal screening and others. And with that, we are going to move now to Dr. Martin Viertelhaus. Martin. Martin?
Yes, hello. Carmen, thank you for this introduction and thank you for setting up this meeting. And also welcome to all of you all over the world. It's a nice experience to know that there are so many people everywhere, and I hope that we can discuss something together on physical stability of agrochemical formulations. I chose a subtitle from suspension to emulsion, as I will show you mainly one experiment where we observed this phase transition in our formulation. So, and that's what I'm going to talk today. I'm going to talk today about solid state properties, as this is probably more or less my background. I will talk about agrochemicals and their formulations. There will be an example on 2 active ingredients plus formulants. And there will be one slide on re-crystallization and what this can do to our formulations. When I talk about solid state properties, this is where I'm coming from. I'm mainly doing polymorph screenings, salt screenings, co-crystal screenings. I do investigations in phase diagrams. And so this is more or less always my introduction slide. I'm talking about solid state properties, and all of you know that different crystalline forms have different solid state properties. And knowledge about these different crystalline forms and about their properties is important for each active ingredient throughout the whole life cycle of my molecule. It starts right in the beginning, but it gets really important in the middle of our life cycle and probably even in the end. What I'm going to talk today is about production of my active ingredient, about formulation, about storage of this formulation, and about application of this formulation. And wherever on this stage, it is important to know which is the most stable crystalline form, which are metastable forms. This might even change when I change the temperature. This might even change when I change the formulation. And this is what I also put into this picture. So when I think about solid state landscapes, I think about an energy landscape of my solid state, and I have different valleys, and each valley presents another crystalline form. And one valley might be deeper than another, and in the end, my crystals, they want to go into the deepest valley. And I also included big wall here, and this great wall might help us to preventing our crystals to swap from one valley into another. Or it can make sure that it really stays in one valley and one crystalline form. And this is how I see formulation. So what is a formulation for? We use formulations to make our active ingredient applicable to where we want to have our active ingredient. Actually, when we talk about agrochemical formulations, in the end, it is about blocking enzymes. So in the latest stage, my active ingredient will be dissolved. It will be a single molecule. But this is not how we can apply our active ingredients on the field. Actually, we can use solutions, but we need go for high loading. We have other requirements for our formulations. So quite often, our active ingredient are solids. These are regular patterns of our active ingredient in crystalline forms. And our formulation, only one part in our formulation is the active ingredient. There are solvents. The solvent might be water. This might be other solvents. This might be solvent mixtures. In our formulation will also be some emulsifiers or dispersants or other formulants. And when we talk about agrochemical formulations, and when we talk about solids and agrochemical formulations, and these formulations might contain a liquid medium where my active ingredient is only slightly soluble, then I have to talk about the most stable crystalline form. Probably some of you have a pharmaceutical background as well, and in pharmaceutical industry, people try to find other crystalline forms. These might be metastable forms which have a higher dissolution rate, which have a higher bioavailability. This cannot be applied to agrochemical formulations where we need storage stability of our liquid containing formulation, and then we only can go for the most stable form. Agrochemicals or pesticides, we have different indications. So the main indications are fungicides, which control fungi. These are herbicides, which control plants. And the aim is to get rid of plants that we don't want to have on our field, and that we support plants that we do want to have on our fields. And actually the same applies to insecticides. Where there are insects, we want to keep away from our field, and there are insects, we want to protect them. The farmer wants to buy a formulation, and he doesn't want to buy a big amount of formulation, but he wants to apply it to hectares of field. So you can see a big field, and you can see how the formulation is, or the tank mix in the end is sprayed on the field. But the farmer doesn't want to buy a big amount of this formulation. So one requisite for our formulation is that the formulation has a high concentration. It is a formulated concentrate. My formulation has to be diluted in water. So we have to have compatibility with water. But this water is not the water we use in the lab generally. It's water from the tap. So we might have also some other chemicals or ions in the formulation in our tank mix in the end, because it is in the water, and we have to make sure that we have full compatibility. And then it has to be applied on the field. And as you can see here, in the end, it will be sprayed on the field. It will be sprayed through really fine nozzles. And these fine nozzles, you will hear about them probably quite some time in my presentation, because when I have crystalline material, this crystalline material has to be so small that it can go through this fine nozzles. And this is one part of formulation development for agrochemicals, that I have small crystals and they don't grow neither in the formulation nor during the dilution process. So that in the end, the farmer can apply this tank mix through these fine nozzles. Yeah, I said before that one thing about agrochemical formulations is that we have high active loading. When we have a liquid, we have to have more or less low viscosity because the farmer wants to easily pour his formulation into his tank mix and has to be good miscibility with water. When it is a solid, it has to be easy dissolved or dispersed in my tank mix without lots of stirring. The formulation has to be stable, and the formulation has to be stable for 2 years at ambient temperature. And there's one thing more about ambient temperature rather than for other applications, because this formulation might be stored in the barn of a farmer. And the farmer's barn is not temperature controlled. So there can be a quite big temperature range that the formulation is exposed to. So we have to think about probably 0 degree up to 50 degree during summer and winter, but also during day and night. There is one type of accelerated stability, which is 2 weeks at 54 degrees centigrade. This is actually more or less from the beginning, it is a chemical stability testing, but it also can be part of a physical stability testing. And this is what you will see later on. When I say ambient temperature is more than just room temperature, it goes to high temperatures, what we tested with a 54 degree storage, but it might also be important to test the low temperature range because there are other crystalline forms might be more stable. Re-crystallization might be more pronounced. In the end, we need to have the application stability. So the formulation is going to be diluted in water. We cannot observe crystal growth. We have to have good mixing, and this, in the end, after spraying on the field, we need to test it for robustness and biological tests. So what is the formulation about all the time? Through its life cycle, we have a look on production. Here we have to think about mixing, different properties, and the viscosity. We go then for storage, and the bullet points for storage are sedimentation, the resuspension, agglomeration, and crystallization. And then the farmer is going to use it. We are thinking about dilution and application. And then it is again about mixing, dissolution, dispersing, and crystal growth. There are lots of different agrochemical formulations. They are listed in the technical monograph from CropLife International. Actually, lots means 63, and I don't know all of them. And I pointed out here all the most important, and in bold letters, the one which contains solid. So my active is solid in a solid mixture, or it is solid and it is suspended in a liquid. Yeah, it also can be dissolved in water or solvent. And then we can have a look on some of these international codes for these different agrochemical formulations. So the most important part for my company is the suspension concentrate, which is called as C formulation. There's this, so this means that it is solid suspended in water, or a water-based formulation. When you have a look for an oil dispersion, then it's more or less the same, but you have it on an oily phase. There can be susper-emulsions where you have a suspension and 2 liquid phases, but there also can be emulsions. These are the different formulations that contain a liquid. You can also have formulations which are fully solid. This is, for example, water dispersible granule or wettable powder. And as I said before, the solid state properties of the active ingredient is important for the whole life cycle of my compound. When I discuss now the formulation, it's also important for the whole life cycle of my formulation and even on the application. So it's important in the formulation, after dilution, during application, and on the plant. There's one more about agrochemical formulations, and this is that the majority of agrochemical formulations include more than one active ingredient. Actually, their formulations they contain up to 4 active ingredients. Why does this happen? And this is because we want to address more than one mode of action. So when I apply a fungicide which only goes on one mode of action, I can quite easily build up resistance in my pest I want to kill. So when I have 2 different mode of actions, when I have 2 different active ingredients, I have 2 ways of protecting, and when one doesn't work, the other works or might work, and the chance to build up resistance is lower. I have a broader application window. One might be better in humidity, one might be better when it's dry. I have cooperative effects of these 2 active ingredients and have a stronger curative effect. Actually, we know the same effect on human beings when we are discussing multi-resistant germs. But when I discuss 2 active ingredients, I have to think about these 2 active ingredients. And this is where I want to come to my example. I have 2 solid state actives, and I just mark them now in the blue cube and the red prism. And what can happen when I only have a look on these 2 solid actives? I can have a mixture of my 2 actives, but I also can have co-crystals of my 2 actives. So, which means here I have a mixture of 2 crystalline forms, and they more or less don't interact too much with each other. In this case, these 2 active ingredients, they form a new crystalline form, and they actually form a co-crystal. So in one crystal, in the crystals, both actives are included in one crystal structure. I have completely new solid state properties. Actually, I can use this type of co-crystal to make new formulations because I have new properties. And I also can have eutectic melt. So what is a eutectic melt? Actually, it's somehow similar to the co-crystal. In the co-crystal, the 2 actives, they like each other so much that they form a new crystalline form. And the eutectic melt, they also like each other, but they don't make a co-crystal. So they melt and interact in the melt. And this is what we observed for one system. And that's what I want to show you. And here is actually the phase diagram of mixtures of active 1 and active 2. So on this line, you see the properties of active 1. On this line, you see the properties of active 2. And actually what I did here, we did lots of several DSC runs, and I plotted the DSC measurements on this in this phase diagram. So just to have a look on this, I have my active 1, and when I increase the temperature, I observe melting of my active 1. And actually in this case, I also see melting of a second polymorph of this active 1. So up to here, I have a solid. Here I have liquid recrystallization to the second polymorph, and then melting of the second polymorph, and then here I have a liquid. The same applies for active 2. I'm heating my active 2. I have a melting point of my active 2, and below the melting point it's solid, and above the melting point it's a liquid. But when I make mixtures of my active 1 and active 2, and I do a DSC on these mixtures, I chose this 90% active 2 and 10% active 1. Suddenly I see the first endothermal event at 62 degree, around 62 degree. And then I go further, and then I see a second endothermal point around close to the melting point of my active 2. So what happened? In this case, here I am in the solid, I have solid, actually I have agglomeration of my two actives, active 1 and active 2. Here I melt, and in this region I have a two-phase system. I have my eutectic melt, which contains active 1 and active 2, and I have crystalline active 2. Up to this temperature point. Above this temperature, I have only a melt which contains active 1 and active 2. Yeah, the same actually applies on the other side. I also observe the melting, the eutectic melting here around 62 degree. In this phase region, I have a mixture of eutectic melt containing active 1 and active 2 and leftover active 1, which melts at a later higher temperature. And altogether, I can see that these mixtures have exactly the same, more or less the same temperature for this eutectic melt. Yeah, in the beginning, when we had a look on this active 1 and this active 2, we had melting points at around above 90 degree and around 80 degree, and we didn't think there might be a problem making formulations, actually making SC formulations out of these two active ingredients. When you have a look now on the whole phase diagram of the mixtures of these two actives, you see it might be hard, because 62 degree is quite low already as a melting point. Actually, it can work, but it can get worse, and that's what we actually observe. And up to now, I only showed you the phase diagram of these two active ingredients, but this is not all. But in the final formulation, we also have solvent and other formulants. And then we have to have a look on the pre-formulation, and in the end we also can have a look on the final formulation, and we might observe further reduction of the melting point. Actually, melting point in this case then would be a conversion from a suspension, the picture of a suspension I showed up in the first picture, to an emulsion. In the emulsion it would be the eutectic melt of my, or the melt of my active 1 and active 2, which is liquid, in this second liquid phase. Yeah, and then, so what did we do, and what do we want to do? And actually we used for this experiments the crystalline PV from Technobis. We wanted to make mixtures of active ingredients in solvents or blank formulations. We wanted to stir them, we wanted to change the temperature, and we wanted to take pictures. And this is the result of these experiments. So we used active 1 and active 2 in a gram per gram ratio. We took temperature ramps of 20 degrees Celsius per hour, and we used bottom stirring for these experiments. And then in solvent A, we observed a small reduction of this eutectic point. So here at around 59 degrees, we can change the conversion. We can see the conversion from a suspension, solid in liquid, to an emulsion, liquid in liquid. Yeah, this actually might also be okay. When we went for a second solvent, which actually is a solvent mixture, we reduced the transformation point even lower. So we are here at around 54 degrees, we can see the transformation from the suspension to the emulsion. Yeah, and now we are actually at the point where we say our 54 degree stability 2 weeks doesn't work. Actually, we don't have to wait for 2 weeks, because when we have this phase transition up to here, and then we go down to room temperature again, we have no small crystals anymore, because we have droplets which will crystallize, and we have agglomeration, we have sedimentation in this case. So what can we say about this formulation development of these two active ingredients? We have the two solids which have reasonable melting points, when they are alone. We have the two solids when they are together making a eutectic melt at 62.6 degrees, which gets in the region of difficult. When we also add solvents, we reduce the melting temperature even below this 62 degree, and we are going into a region where we say we need to have stability at 54 degrees, so it doesn't work. And actually, in this case, there also was done a first formulation, and the first final formulation, this first final formulation showed that it is physically not stable, that we observe agglomeration and sedimentation. And in this case, actually the decision is quite easy, and by this few experiments, it can be done quite early that suspension concentrate does not work for these two actives together. This is a sketch where I extended the picture from before. Now I have the active 1, active 2 plus formulants, and in this formulants I also added the solvents. So what is possible at this stage? I can have the mixture of two actives, both crystalline in liquid, which is an SC formulation. I can have the co-crystal, which contains both of the actives and which is suspended in my liquid, which is also, when the liquid is water, is also an SC formulation. I also can have, it's possible that the active 2, for example, is completely dissolved in my solvent, and then I have solid active 1 in solution of active 2, which is also, if it is a water-based suspension, in a C formulation. And here I had to split up. So what can I have in the active 1, active 2 regime? I have the eutectic melt. That is what we saw before. But when I when I add the formulants, this might be a solution then in this case, when these two, the melt and the solvent is fully miscible, or it might be emulsion when it is not miscible. And that's what I just showed you before, what we observed in the case of this active 1, active 2. Yeah, when I observe this kind of phase transition at a too low temperature, I observe recrystallization, agglomeration, and sedimentation. It might be even easier to observe this, and this is then another point. Actually, in this case, I showed you some pictures which are not taken by formulation development, but which are really nice to see what difference can be possible by just a few degrees centigrade. So we here as well, we did some temperature cycling, and actually temperature cycling is what you observe in the farmer's barn, where you change the temperature during day and night and during seasonal changes. And by this, crystal size, crystal growth, and changes in crystal morphology are quite possible, quite likely to happen. So you have to make sure that the formulation does not allow crystal growth, changes in crystal morphology. And it's quite nice to have this type of equipment to make where you can make different individual experiments with individual temperature programs. And here in this example, it's just an excerpt of a big size of pictures where we observed recrystallization, actually crystal growth, in a really small temperature range. And in this case, the temperature ramp was 7.5 degrees per hour, and we also used bottom stirring. So to summarize, when I have a look into physical stability of agrochemical formulations, it is for me investigations about the solid state properties of my actives, then this investigations regarding model formulations, and finally the final formulation. By using this approach, this type of bottom-up approach, I can do quick decisions right in the beginning rather than running with the wrong horse. When I did these experiments in the beginning, or also I might do them later, I can explain observations of farmers and users in the final formulation. I also can try to mimic experiments or observations that users did later on. But it is quite good to know what my formulation does, how stable it is, when it is stable, and where it's out of the stability regime. And this is really good when we can do this right in the beginning to early decide for the correct formulation type to develop. Yeah, we can, with these pictures, we can observe dissolution, recrystallization and crystal growth, and phase transformation. And I think this is quite helpful in doing formulation development. This is, I presented now this work, but this is sure it's not only my work. There are lots of people behind. Experiments that are showed here and also a consultation that are showed here. I have to thank especially to Christian Sowa and to Rolf Hellmann. And I also want to thank Carmen for setting up this meeting. And I also want to thank you for listening. I hope it was interesting for you. I'm looking forward to your questions. And by this, I give back to Carmen Guta.
Thank you, Martin. If there are any questions, you might want to send them to info@crystallizationsystems.com, and we will try to address them afterwards. Thank you all for your attention, and we look forward to welcome you to our next webinars. Goodbye.